Okay, hello everybody. I'm William Gomez, as Milton says. I'm a full stack engineer in Huge Inc. I am also a co-organizer of Python Medellin. I am the one who brings the pizza to the events, kind of. I started like in that way. Then I started planning the events, to recruiting like the speakers. Then I want to talk a little bit about my background and university. Well, I was professor at the University of Antioquia until the last semester. I also was a PhD student of clustering algorithm. I decided to quit because the money, no, I'm kidding. I decided to quit because of personal reason that we can talk about the talk. But this is kind of the way I arrived to these topics, to clustering, to machine learning. I've been working for this like 5 years, so that is it. So the talk is AUREAS, which is an algorithm tool that is used for unsupervised species recognition. This tool is, the name stands for animal automatic recognition of animal sounds. Okay, the talk is divided in what is AUREAS, the first software that we implement that was developed on my lab. The second software that was a server-side application that one of my students developed, and then the desktop app that is the current application that we are developing. And I will talk about that later. But I will start with AUREAS, but first I want to ask you one question. Who the hell wants to work with frogs? I mean, I'm an electronic engineer. Obviously, biologists, obviously, herpetologists want to work with frogs, wants to know how many frogs they have in the forest. But who else? I didn't want to work with frogs. I started looking for my thesis, and I saw a poster that says, hey, we are looking for students that want to recognize frogs. And I just said, no, I want to do that. And I didn't. I wanted to do cool engineering stuff, like intelligent systems, like creating control systems. I didn't want to work with frogs. After a while, I couldn't get a good enough thesis in machine learning, so I had to work with kind of similar stuff, that is bioacoustics. Bioacoustics is analyzing the sounds of the ecosystem and determine if the ecosystem is behaving well or not. So I did well my thesis. My advisor told me, I'm going to hire you to develop this software that was with frogs. I didn't have money in that time, so I started. And after a while, I started, my family started to see me in my house, listening like frog calls, like environmental sounds, and they said like, what are you doing? What are you doing? And I don't know, maybe it's because I get passionate easily with the things. And I started to develop this, and I get like some love for it. Well, before I start, I want to bring here the human problem that we are solving. That is, what is biodiversity? Biodiversity is the study of all the variety of life on the Earth. Studying what are the species, what are the genies, what are the microorganisms that we have, and what are the different ecosystems we have. So, okay. So what is important? You know what is important. You know that we need to care about the nature. But to bring here some metrics, 40% of the economy of the global world depends on that. 80% of the needs of the poor people depends on biology, relies on biological resources. So this is a thing we need to study. We need to we need to determine how to prevent, how to care about it. So to study biodiversity, we are interested in determine how is the ecosystem structure? To do that, we need to do some biodiversity studies. The first one is the passive monitoring, and the other one is the traditional monitoring. Traditional monitoring is what we could say that we mark some species in the forest, we send to some biologists to count the number of species, and this could have like more cost, more effort, while passive monitoring is like a new trend that allows us to collect remotely data with the benefit of those new sensor technology that allows us to do that, to just put a recorder in the forest and record some recordings that we can analyze after a month. In the passive monitoring, there are three topics in the literature. There are the satellite images, visual monitoring that is putting a camera in the forest, and the final one is the bioacoustics. We focus this work in bioacoustics, more specifically in a species call recognition. Why? Because it allows us to analyze all those species without catching them, without manipulating them, without having contact with them. And it also allows to monitoring all those species in large period of time analysis. We have also, we can deal also with those species that have low detectability, those species that we cannot see but we can hear. It is cheaper. We only have to put, as I said, a recorder in the forest, and that is all. After that, one biologist can analyze the recording, or we can just set an automatic tool as this one. What challenges in percent? Having, for example, some species that are overlapping in the frequency. So we need to find a way of determining if two species are overlapping and try to separate them. Another challenge is having a species that have different kind of calls. So those species has like high within group variance in their calls. And also the environmental nodes, like having a river near to environment we want to analyze. Okay, the AUREAS is this. AUREAS is some of the common steps of the classical approach of species call recognition, or I could say voice call recognition, where we have recordings. We segmented those recordings because we want to focus the analysis on the possible cause where the species can be. After that, we can extract some features. And finally, we can do a classification. The feature allows us to translate this real world to a point in the space. And after that, an algorithm can separate them. And we can identify this happy frog that was identified. After all of that, what biologists care about, because as I said, we need to implement tools, but the human problem is the real goal of everything. We need to extract insights. What insights? Is the species calling? Is the species calling in this area? Is the species calling at which time of the day? So this is the real part, the real focus of this work. I'm gonna talk about each stage, and then I will present the applications. The first stage is recording. We have this kind of special recorders that are kind of rugged for these conditions on the forest that have for example, a high humidity. We set those recorders in a central part of Colombia, in Antioquia. This is not central part of Antioquia. So we set the recorder and put it near to a dam of Isagen. Because Isagen wanted to study that zone and determine if the dam affects the ecosystem. At the end, we have a recording. We have a signal, and we want to analyze that signal. To analyze that signal, what we do is to compute the spectrogram. The spectrogram is just like the same signal, but for each unit of time, we have the components of frequency that that unit of time has. So maybe you cannot see nothing here in this image. I've been working for this like 5 years, so I can see here like a bug. And here there are some frog species, yeah. I can identify 12 kind of frogs. So, okay, it doesn't matter. The thing is, from the spectrogram, we need to extract the relevant portion where we can like extract the feature without noise. So we do segmentation. The segmentation was done using integral projections. So along the time axis, we do a max projection that tells us which bands are more relevant. So for example, we have here a high amount of energy band, and we have here another band. And after that, we can select the bands. For each band, we can select the time step. And it's the same thing. We do integral projection, that is the sum of all the energies along each unit of time. And we end with this plot. This plot tells us that here we have a big cold. Here we have maybe possible colds. So what we do is to get these two plots and identify the lower peaks. And with those lower peaks, we can set threshold. That threshold allows us to determine which are the intervals of the bands and the time steps. So we end with this, a call or a frog, or maybe noise. So that's why we extract some features. These features are based on the Mel frequency coefficient. I don't know if someone knows that coefficient, but the thing with that coefficient is that they apply some filters. Those filters give us like the idea of what amount of energy we have in each band of frequency. In this case, we are only concerned about the call. So this filter will tell us that we have enough energy here. So we can have, well, first of all, before applying these filters, we split the signal in frames. So for each frame, we have these filters. So it's like a compressing of the image, kind of, could be. After applying these filters, we have some features, and those features are sent to the classifier. What does the classifier is to create cluster. It's not a common classifier that determines this sample is from this cluster or from this other cluster. What it does is we start with 0 clusters, use one cluster that is the NIC class. The NIC class stands for no identified class. So that class is a class that each point will fall in that class with the same probability, 0.5. So if a point falls in that class, a new cluster is created. See, if the point falls in a cluster, just is assigned to that cluster. So we have the features. This algorithm works in this way. We have some marginal function. That marginal function, don't be afraid. That marginal function are just like a probability of that specific feature or the data point belongs to the cluster. So we have, if we have n features, we will have for each cluster n math functions. That means marginal adequacy degree. That is like a probability, and we integrate all those math functions using a get function that is just an integrative function. I know this looks weird, but it's just think it like a multiplication of the probabilities. Okay, so it's just like at the end computing the probabilities for each cluster. If a sample falls in the NIC, a new cluster is created. So that's the algorithm. So at the end, we can have this insights. We have 4 species that we identify with the algorithm, and we have the representative calls. What is a representative call? We have for a cluster a number of calls, but the call that is the closest call in the space to the center of the cluster will be the representative one. So we have those inside. We can say like, this cluster, the time duration of each call in average is like 0.3. So that's our insights that the biology are interested in. We can also extract like, we have a species and we want to know if the species called in the day or in the night. So for example, this plot was done by a biologist listening to the recorders, and this plot was done by the algorithm. If you notice, well, we have here like different colors because we have different clusters for a species. But if you know here, we can extract the same inside. The species is calling only in the night, has more calls in the night at the 10 o'clock could be. So I know that if we are talking about machine learning, everyone wants to know about the metrics. So the metrics are, we set first a data set with 6 frog species. So for each species, we have this amount of calls. If you notice, this data set is unbalanced. So we need to set like a metric that can handle that kind of data set. So that's why we set the F1 score. This one score is just a metric that tells me if the algorithm is identifying the species with a high precision, and if the algorithm is sensible to identify that kind of class. So that's the precision, and recall could be called also sensibility. Okay, so this is a harmonic mean that could be, you can think that as a average. So this is the F1 score, and for each species of the classification with a cross-validation methodology, we end with these metrics. You can think that these metrics are kind of low, but in the practice they work very well. Even the average score is 0.72, and think this is a clustering algorithm, which always will have less accuracy than a supervised technique, but it allows us to identify new things. That's the advantage. I will show you the MATLAB software, so wait for it. Wait for it. So this is it. Nice. I have to do the same with everything. So this was the first software. This software was implemented in MATLAB, and we can select some species. We need first to train one species. To train a species, we can set like 2 folders of recording, obviously. So we have a folder for the training, and we have a folder for the test validation. It's like a weak validation, but it works pretty well to know if the cluster is working. We select, for example, here the range of frequency that we think that the species can call, and it delivers us these results for each segment to which cluster it belongs. So we can have more insights, like the full spectrogram. We can have, for example, the representative calls of each cluster. So if, for example, we have these representative calls, and we know that this is a colostatus species, it's because a biologist knows. This is a tool for biologists. So we can see if all the elements of that cluster belong to that species. If it does, we can just save the species. We can also see if this cluster is near to other cluster based on a metric of similarity that is displayed in that dendrogram. So for example, here we are saving another cluster that, as you can see, have the same species. We can then use the test folder and just see what the algorithm recognizes. So as I told you, there is an E class, there is a colostatus 1, colostatus 2 class, and we can plot where the software identified that species. And we can have more plots, like how is the distribution of the points regarding to the minimum frequency and maximum frequency, the duration of the call, and as I have been telling you, the activity pattern of that species, with with a high amount of recordings, obviously. So that's the MATLAB software. Let me think if this works. I know what you are thinking. MATLAB, it has some problems. What? We cannot publish that. We have a software that only can be used in the university. You cannot publish that. MATLAB has like a ugly UI that maybe you can configure. I never seen like this configured, but okay. So we decided to move this to Python. Well, we decided no. I was giving my course. In my course, we have a project. We have a project of the course, and I tell to one of my students, why not you translate this to Python. Could be. So sorry, but it works. This was my student that translated it to Python. He implemented a server app using Django. This is the result. OK, this is the tech stack that we have a Django application where the Django, what it does is to render some views and providing some services. We have also signal analysis using SciPy, where we read some audios, and we obtain the spectrogram using built-in functions. We have NumPy to extract the features, to extract that segmentation that I told. We have Matplotlib to plot that kind of pretty plots. As the time was short, I tell him, use a clustering algorithm of any library. So he used scikit-learn and implemented the k-means. So k-means. So and like it has a UI. It was implemented with Bootstrap. As you can see, we have here like a full stack software that actually is pretty simple. It has the reading of the files. We can extract the segmentation. We can do. We can extract the spectrogram, and we can do clustering algorithm. To be honest, this software is kind of incomplete. It works more or less, but that's why I decided to get from something from them and implement a desktop app. That desktop app was done like, sorry, I love Python, but I also love doing web application. So I decided to implement a desktop application using Electron.js that is like a cron engine that allows us to put a web page as an application. That's all. I did a React application. That React application was connected with Redux. And Redux, what it does is to control the state of the application in every moment. Also, I use a component library that is supposed to be used to minimize the work. That put like kind of good styles, I could say, but you have to do a lot of work with that. Chart.js is used to plot in the data as we have in the MATLAB application. For the backend, because we have a local server, because it's an application for the desktop, I use Django because it's simple. And it was used for routing and for the views, for some views of the controller. So I use also the Django REST framework to that parsing of the body of the request. The same thing, SciPy for audio analysis, NumPy for matrix operation. As you see, the spectrogram is just an image and matrix. So we can, with NumPy, apply all that stuff. With Matplotlib, we plot, and I did an algorithm, the Lambda. I programmed it, so it's open source right now. And you can use it if you want. This is the app. I could say it's OK. I'm ashamed of this because I'm from an agency that do pretty well designs. But as I didn't have a designer, I did it. So this is kind of material UI. We can select some files. We can select the species. And that's the application. To summarize, I want to tell you the flow of the application. We have the Electron.js to render React. Okay, we have Django to request to the server which are the species that are saved. We have also Django to look the folder of species. We upload to those files to be read by the servers. We use SciPy to read the audios and compute the spectrogram. NumPy allows us to obtain that projection that I told you. Also, with NumPy, we can extract those features. As you see, the features are, we have the spectrogram, we have the call, and the features are triangle filters. Those triangle filters are just a matrix operation. So that's why we use NumPy. Also, with the algorithm, we implement the lambda with NumPy. Finally, React Reduce display the results. Chart.js uses to plot in data, and after, at the end, we use React to send which segments are relevant, and which, with Django, we store the cluster models. So that's the application. I will show you a short demo. If you want, you can do the question in Spanish. I thought that this was going to be like some English speaker, but I can see that there is no one that speaks English here. Oh, Christoph, okay. You can do that, the question in English better.
No, it's fine. So you keep saying that it's a clustering algorithm, but you compute the metrics like as if it was a classification algorithm. And also, you keep saying that the clustering algorithm gives you the label, like the actual species, but it's not possible for clustering. So it's a bit confusing.
Okay. Okay.
So what is it? It's clustering or classification?
The thing is, to get a metric, the first approach we can use is like having the same approach that we have in classification in supervised learning, that is doing a cross-validation, and just like to each cluster assign like the real label, could be, with the mode, with the frequency of the labels, could be, kind of. I mean, we have the label, we have for each cluster a set of elements. For each element, we have a label. So the mode of these elements is like the real label of the cluster. Could be, yeah. I know that this is not the way to test it, but what's the first approach? To validate cluster is kind of difficult, but you can use other kind of metrics, like unsupervised metrics that only tell us if the cluster are compacted, if the cluster have separation between them. So it's pretty difficult. That's why you have to provide like a supervised metric. There is no other way, like a way that someone will believe you. Yeah. And the second question was, I forget it. The second question was, okay, we have the segments. Obviously, you don't know if the cluster 27 belongs to that species. That's why we provide to the user the representative element. So with the representative element, you can see if that cluster is kind of, it worked for me.
So it's more like finding the most similar representative element in the dataset, right?
Yeah.
Okay.
So as we generate a cluster, as you see, the first cluster was the 27. It was not like random. The first cluster was the 27 because was the cluster most compacted. So that's a tool that helps the biologists to analyze quickly that. So this is the tool. We can store, well, this is the species. We don't have a species. We can have, as I told you, test and training. For training, we can set some recordings. Obviously, we can have more recordings. This is just a demo. We can add a species. So it starts requesting to the Django server. I hope this works. It starts requesting to the Django server. It is okay. It works. So this is the kind of the same interface we had in MATLAB. What I tried to improve the UX. Right now we have the representative calls over here. We can see for each species, for each cluster, all the information in just one view with tabs, obviously. We can have plots of how the points are distributed in the space. We can have the same plots. We can have the same in size. We can also have the theory patterns of the recordings. Oh my God, Matt, why? Okay, I finally did it. Okay, we have the same patterns. As I told you, you have to have like a great amount of calls. And we can store one cluster. For example, I want to store this one that has the call I know. This is because, obviously, as I told you, I know where are the calls. These have to be handled by a biologist. So I can store this cluster. I can see here. is all the code of this cluster belongs to the species I want to analyze. For example, this has the call. As I told you, this is a demo, this is in progress. They have some difficulties in the segmentation. The MATLAB software is working pretty well if you want to test it. But this is the open source that I want to keep working. So I can save this cluster and identify that I create the cluster. I can go back. I go back and I can test this species in the test folder. Call status, test. And I can search right now instead of adding a new species. And this is the results. We have the nick class that are calls that are pretty long, so the software is not showing that. We have the call status. As you can see, identify well in a new audio the species. This is keeping working in progress. So that's like the future work, improving the UI, improving the UX, improving the state of the application, because as I use Django to handle all the data processing, I had to do that with REST methodology. So it has to know the state of the application in every moment. So all of that is the future work I need to do. So you are welcome if you want to work in this open source project. Anyone has a question? Christoph, why? Why, Christoph? Why? You can talk about that later.
I just thought of one. Okay, is it possible to reuse the software to discover or cluster other things than just like animals? Like animal species, for instance, to use it to verify if an engine is working. Like if you would have a set of recordings of a working properly configured engine in a car, and then you would try to discover like if there's a faulty one because there's a something tinkering there or like a noise somewhere or something like that. Is it possible to like reuse this for other applications?
Can you repeat me, please? I'm kidding. Yeah, you can use it. But the thing with this is that, as you see, these calls are monosyllabic. So they are simple calls. When you have like an engine of a car, you have a lot of those, how can I say that, all those segments of those energies sparse in the space. So the software will be, but at the moment it cannot do it. Because you need to correlate if this segment that is in an advanced moment has relation with the previous one. Yeah.
Hi.
Hi.
My question is about the data set and what were your experience about the dimensionality of the data set, because when you transform the data that you collect in the input of the algorithm.
Okay, so if I can summarize, it's like you are concerned about the dimensionality of the data set, the amount of data, or just the dimensionality?
About dimensionality.
Okay, to be honest, you can identify some species with just few features, like the dominant frequency, like the minimum frequency that has the call, like the maximum frequency. But when they are in the same frequency, you have to put this kind of feature like FCC, the melt frequency coefficient, that you can select the amount of coefficient you want. In this algorithm, I use like, I think was 10 coefficients. For each of them, I compute the derivative because it's important the time of the frames. And the second derivative. So there are 30 coefficients in addition the metadata. So there are like 40 coefficients. So I could say that for a clustering algorithm, it is kind of killing it, because for a clustering algorithm, you have to have the relevant coefficients, the relevant features. So this is all the process that needs to be done to reduce the amount of coefficients, like to reduce that to 10, maybe, yeah. But it is working right now with these coefficients. And the get function that I told you, that tries to integrate all that amount of coefficients. So that's why it's working kind of fine.
Yeah, just one question. What happens if you have multiple frogs from different species doing the same noise at the same time? Do you have different microphones also in the same environment, or just one microphone to take all sound?
Well, the happy thing with this is that most of the frogs calls in different frequencies, always. Why? If they don't call in the same frequency, they call in separate space of the time, because it's like a rule in the nature. You cannot like use the space of the other. So if the frog call in this moment, the another one will call in few seconds in the future. So yeah, it would be a problem if they are overlapped. Yeah, it will be a problem. You will end with another cluster with that kind of overlapping. So it could be useful, but the real goal is to separate them.
Yeah, so if you have, let's suppose that you have two different species doing their calls at the same time. How do you know, or how can you separate those sources? Is it the diarization problem? I mean, it's like you have only one microphone, you have only one source.
Yeah.
It's not possible to split out
It's not possible.
the different sources.
It's not possible. That's why some approaches in the literature is to use some microphones and triangularization, I think is the word in English, and try to identify them in the location, and also you can split the audios, obviously. Yeah. When you use one audio,
If the species are different and they talk differently, then yeah, it's possible.
could be. It depends on the problem, I think.
Talking with background noises is the same thing. But not exactly.
You can also have like a correlation of the time of some species calling before, and then try to erase that species from all the spectrogram and return all the rest of the species that is calling in that time. Could be.